Hi, ladies and gentlemen. This is Bingxu Chen from Henan University in China. Today I'm here to introduce our work about an orbital angular momentum mode estimation method with a known beam axis. One beam has a helical phase wavefront and a divergent beam, so it's very difficult to detect OM mode in full aperture. Phase gradient method is reported that can be used to estimate the OM mode. However, all current OM mode estimation methods require the position of beam maxes to be known. So here we propose an OM mode estimation method with a known beam maxes. The phase of OM beam is expressed as this formula. The phase can be divided into two phases caused by free space and by the source. For the phase caused by free space, the isophase lines are concentric circles with the beam maxes at the center, as shown in the right figure. Based on the geometric relationship and the definition of the isophase lines, the phase change caused by the adjacent phase line is 2 pi, as shown in these equations. According to these equations, we can solve row 2 and therefore estimate the beam maxes. For the phase caused by the source, the isophase lines are the rays that radiate outward from the beam maxes, as shown in the right figure. Now we select a rectangle sampling area for measuring the E field. If like this formula, the azimuth angle covered by the sampling area is very small, so the phase caused by the source, L phi, can be regarded as a constant. As a result, if we don't know the position of the beam center, we can estimate the beam maxes first, based on the phase caused by free space, and then calculate the OM mode by the phase gradient method.
According to the basic principles introduced previously, we propose a new method to estimate the OM mode with a known beam maxes. The flow diagram of the proposed method is shown in the left figure. First, the phase pattern of the OM beams in the far field are generated numerically. The phase plane is 10 meters away from the source antenna. Then we sampled the complex E field in a rectangle area far from the beam maxes, and then performed a two-dimensional interpolation on the sampled E field. Next, based on the interpolated E field, we choose 3 suitable adjacent isophase lines to determine the coordinates of the beam maxes according to the rule 2. And finally, based on the coordinate of the beam maxes, the OM mode is estimated with the help of the phase gradient method. The histograms of the estimation results using the proposed method are shown here. For the transmitting OM mode L equal to 1 and L equal to 2, the beam counts of values 1 and 2 reach the maximum. The conclusion is that the proposed method can effectively estimate the OM mode when the beam maxes is unknown. Future work will focus on conducting experiments and analyzing the errors of each step in detail. Well, this is all we presented.
Thank you for your listening. Any question?